Okay, I guess we can start. So basically, what I was going to do today, just was to give you a couple of examples of like these simplicial complexes, how they arise, so that you see that they are like a very like kind of like natural construction in many situations. Um, Maybe let me just remind you what we were talking about last week of how they're defined. Um, Let's see. So where should I start here? Okay. So yeah, this was like a good example, the one we were working with. So there are two ways to think about the simplicial complex. One is kind of like more like sometimes like you can refer to it as combinatorial or discrete, and the other one is more like geometric. So kind of like at a broad level, if you think about it, kind of like in terms of like a list of data or like discrete information, what the simplicial complex does is kind of like first it's characterized by some vertices or nodes. So in this picture, for example, there are four vertices, right? So every simplicial complex will have you know, kind of like at the base, some vertices that define it. Okay, and then the idea is that there are certain relations between those vertices that are captured just by listing those relations in terms of subsets. So for example, here I'm listing the subset V2 comma V3, right? So I'm interpreting that as saying somehow V2 and V3 are related. And pictorially, if you want to, you can represent that relation by drawing an edge that goes from V2 to V3, which is, you can kind of like see here in the in this picture where I have it here. So again, the at a kind of like in the way you would type it on the computer, of course, you wouldn't draw the edge. You would just enter the subset, V2 comma V3. So at a combinatorial level, the relation is just being described by just saying which two elements you're relating there. And the same goes with the other four edges that you see here. So again, there's kind of like this geometric picture if you want that you can always go to if you want to kind of like have like a more concrete thing in mind. But the list itself is kind of what defines a simplicial complex. And for example, in this case from last time, again, we were thinking that V0, V1, and V2 were related somehow, and because the three are kind of like simultaneously related, you reflect that by a subset that contains V0, V1, V2. And because it's kind of like a three relation, right? Like the usual relations, like in mathematics, that most of the time are kind of like what you call like binary relations between two objects. But this is kind of like a three relation. So like a ternary relation would be a name for it. I think the example I gave you last week was like, oh, you could think that three professors are related if they authored a paper where they are like the three authors of the paper. Okay. Uh, so again, that's being reflected pictorially if you want to by drawing, like filling out this triangle. Um, but at a kind of like at a more like discrete level or like just like from the perspective of um, of the data, the simplicial complex consists of some like underlying data points, which are like these vertices or nodes, and then subsets built out of those vertices. Uh, what it's not just any collection of subsets, right? That's where you have to. That's what will make the simplicial complex interesting because it had this closure condition. So again, what did the closure condition meant? Well, so you can just contrast it with this other picture that I have shown you, where it is almost exactly the same as the one I had before, but I deleted this edge, right? Like this edge that goes from V2 to V0. So if you look at it in terms of the list that we have, now there's no subset that represents V2 and comma V0. Okay, so the reason why this is kind of like not a simplicial complex from our perspective is because if you look at this triangle, right? The triangle is still part of the simplicial complex, but now the triangle has pieces of it or subsets of it which are not listed. right? So because for example, the subset B0, comma B2, which inside the triangle is not listed in the complex. So essentially what the closure condition says is that the moment a subset or the moment a set appears in the simplicial complex, every subset of it must be listed as well. So kind of like the simplicial complex contains like all the subsets of a given set that belong to it. Um, which and again in a pictorial way, you in this case, like if you think of the triangle as having three edges, and what that means is that like all if once the moment the triangle is part of the complex, the edges must be part of the complex and the vertices must be part of the complex and so on. And if you had like a tetrahedron, which is kind of like a pyramid, the moment the pyramid is inside the complex, all the faces of the pyramid must be inside the complex, all the edges of the pyramid must be inside the complex, and the vertices of the pyramid must be inside the complex as well. So in the example that I was giving you with the authors, right? Um, like in this case, the reason what this one was a simplicial complex means that if the three professors had a paper where they are authors of a paper, then they also did write papers pairwise. So two at a time wrote their own paper to get they wrote three papers in pairs, and also each of them wrote a single paper because again like in the simplicial complex everyone if you have the triangle the vertices must be present as well, which is means that the professors have their own papers where they're the sole author of it. So it is not any random relation, right? Because you could imagine people that only publish together and never by themselves. So it is more like restrictive than just like any relation between individuals or like other things. But in mathematics, usually you have to have extra conditions like in order to get something interesting. So this will prove to be like an interesting condition, and that's what we'll kind of be talking about more or less for the entire course, because like essentially the strategy for the course will be kind of like to associate simplicial complexes to different things, and then you just apply the machinery being to compute these matrices, which I still haven't given you like the full recipe for combining these matrices, these Laplace matrices that I called last time, but I'll probably do that more of that like next week, or like maybe even next Thursday. What I want to do for today is more like just to give you examples so that you see like that these complexes do arise like in many natural conditions, you know, um, which is good to know. Is that okay? So far, so good. Any questions about this? Okay, so let me give you. So this is like a fun one. Okay, and it's like a very useful example. Where which one should I start with? Oh, sorry. Okay, so I'll start. Okay, so as I was saying, for today, I'll do today like examples of simplicial complex lists. So the kind of like one of the most important ones is called the check complex. So okay, so this is kind of I think it's like a Polish name. So you kind of like you have to write the E with this like symbol. So this is called the check complex. And now, like, kind of like motivated by an example, which you can think of it as concrete, which I had mentioned before, like this sensor coverage problem. So here's like a motivation for this complex. So, like for example, you could like you could have like a forest, you know, you could have like a forest, and you have like some sensors, like kind of like smoke detectors or something like that, just to make sure like if there's a fire, do you have like some notification that there's like a fire, right? So you could imagine like trying to cover the forest with some sensors, right? So I'll write the sensors as nodes or dots, right? So I'll draw my sensors as I'll draw the sensors and so as some sort of like some sort of dots in my picture. And then, like a sensor, like, you again, like you could imagine, like it only, it can only detect this fire or like that smoke within a certain region, right? It has like a mile range, right? Like, so you could, by the way, you could even pretend that you don't know precisely where the sensors are placed, right? Because maybe there are like animals like that grab the sensors like in the forest and they just move them around, like squirrels or whatever, like depending on the shape. So like maybe the location of the sensors may not be completely known to you, like or within some margin of error, right? Uh, But kind of like the idea is that, you could imagine kind of like each sensor has like some sort of like coverage region that it can cover, right? Where it could detect the smoke. So you can draw, like I'll draw them kind of like as balls or discs. You don't have, it could have like a more weird shape, but just kind of like, let me try to draw some discs. Well, I mean, if I could, if I try to make a better picture, like I'll try to draw the discs so that they look like more like being centered at each of the sensors. But again, like you could imagine like that not necessarily being the case. In fact, let's pretend that this one has like a lot of like mileage. It's like a more powerful version. Okay. Okay. So that's kind of like one of each of these like circles kind of like represents like the again the what each of the sensors can where each of the sensors could detect the smoke, right? And like there are like even just like looking at this diagram, right? It is kind of like more or less like it is more or less clear that there's wouldn't cover the forest completely, right? Like there is a massive hole here, that like where there's no every that is outside the regions of any of the sensors, right? So here's a kind of like a hole like I'll put whole in quotes, right? Because again, this kind of the point of the course is to make more precise these ideas. What do you mean when when you say that something has a whole or not? Okay, so this is kind of like the whole, right? And like in like these sensor coverage problems, one of the things that you may want to know is detect whether, there are holes of that sort, like, whether because it means like the coverage is not perfect, right? So you would one of the goals, like, of topological data analysis, um, would be to detect whether like, like the sensors like lack coverage in this way. So one of the goals, whether you know, there are holes. Or again, I'm being like ambiguous on purpose, or like areas which are not fully covered. Okay, so far so good. And the idea is that again, there is a kind of like a machinery that you can apply here, which involves like this Laplace matrix, like simplicial complex, which will can compute whether there are holes or not. Now, just to kind of start defining some notation, like essentially, what you would like to first, like again, my point is that you can kind of like create a simplicial complex out of the sensors, like the sensors network. Also, you can think about this like as coverage, like AT&T or Verizon, like T-Mobile, like they have like all these like antennas, and there are similar problems that you could imagine in that case, right? So like the idea is that you can create a simplicial complex determined by the sensors and their coverage and the area that they can cover. cover. Okay, so I'll show you how that works in the next page. I just have to introduce some notation here. What else? But it's like a very elegant construction, and it's again a very useful idea, which appears in many other situations, not just this one about the sensor analysis, but I just think it's like a very concrete example that motivates it. So let me see if I can. So my first step is that, I'll just label the sensors. I'll label them in a completely arbitrary way. So to kind of like emphasize it's arbitrary, like I'm not even going to kind of like number them in a way that feels ordered, right? So I'll just, I'll call this one um, V0, and this one will be V1, and then this one will be V2, and then this one could be V3, and then this one could be V4, and then this one could be V5, and then this one could be V6, and then this one could be V7. Right, how many do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. Did I for okay. V0, V3. Oh, right, because I started at, oh my God, I hate this. Because I'm starting the indexing at 0. So yeah, if I stop at V7, I do have like 8. I have labeled the 8 of them. Yeah, it's annoying, but it is convenient to start at 0, like in these problems. Okay. So again, this is kind of like the node, the vertex set. So one for each sensor, basically. And again, that's kind of like the structure out of which you build a simplicial complex. Okay, so in this case, the vertex set consists of all of 8 nodes, right? Consists of 8 nodes, one for each sensor. And so, like, kind of like you would say that you would draw in the simplicial complex, you want to include let me just say pictorially, and then like I just will draw the list. You would say that you can draw an edge between the two of these sensors if there's some overlap in their coverage area. Okay, so if there's some overlap of the balls, like what looks like a ball, like intersection, if the balls intersect, two of the balls intersect, you would draw an edge between those two corresponding sensors. So it's kind of like, you can imagine that kind of like a sensor can detect another sensor if it lies in its coverage area. So like that, if the sensors kind of like detect each other, then they kind of like you draw an edge for them. So you draw an edge if the coverage area of the corresponding sensors overlap. So for example, here, right, what do we see? Like for example, V0, and again, you can, let me, I don't want to, I want to do many versions of the same picture so that it's not all like on the, so for example, oops, uh, V0 and V3, right? They do share like some overlap regions, so there's an edge between them. Same goes from V0 to V5. Same goes from V5 to V2, right? Same with V2, V6. Same with V6, V7, right? V7 also intersects V1. V1 and V6 also intersect, right? Because there's kind of like a big overlap there. Uh, V3, V4, right? And then V4, V1. Okay. So that's kind of like how the region looks like, like all these edges look like. But again, that is kind of like a picture for you to kind of understand the situation. You can totally just write those relations as a list of subsets, right? So like the subsets would be, just to say V0, V3, and then V0, V5, and then what, V5, V2. And in fact, like we can discuss later how to, compute all of this on the computer. And that's literally how you would enter the simplicial complex. You just write a bunch of subsets that kind of like determines all the relations, V2, V6, and then V6 with V7, and then V7 with V1, and then V6 with V1, right? And then V4 with V1. I think those are all. I don't know if I don't have V3 with V4. Actually, I don't think I have V3 with V4. So that should be all. So I have 2, 4, 6, 8, 9. And how many edges did I draw? 1, 2, 3, 4, 5, 6, 7, 8. I think we're good. So and I end up having 9 edges. And again, I can draw them pictorially, but I can just also draw them as a list of like numbers. Okay? So far so good. And hopefully you can like see where I'm headed with this. So for example, if there happened to be like, this is kind of like a pairwise intersection, what I'm looking at here, but I could also look whether there's like a triple wise intersection, as in like, if three of the coverage regions like intersect, then you would associate to that a solid triangle. So like you fill out a triangle. So that would be the of the coverage regions I meant intersect. So in this picture, I mean, like here, like I'm just, if they touch just barely, like kind of tangentially, like that I'm not considering as an intersection. So like meaning like there's actually some area trapped between the two regions. Again, like you could be basically because just to not throw too much terminology, but here like you kind of like cover it by open sets. So kind of open set is kind of like something where like the boundary is not part of the region. Um, but again, like for like just kind of trying to develop an understanding, you know, in this case, the only one where like there's actually an overlap of three regions, right? Okay, where overlaps of three regions. Oh, actually, I didn't finish drawing all of them, right? Because I guess V2 and V1, right? V2 and V1, they also have like an overlap region, so I should draw an edge. I'll fix that. And okay, so let's do that before I continue. So let me put here. So well, of course, like I could have drawn a nicer picture where it would have been easier to see all of those things with multiple colors and what have you. But yeah, V2, V1, there is a shared region as well here. And I do, okay, let me see. Now though, I should double check everything again because I think now we are good to go. Okay. So where are three intersections? Like, so for example, the region of the coverage region of V2 and the coverage region of V6 and the coverage region of V1, right? They do have like a triple intersection somewhere in here, right? So I can draw, I'll call, so just to zoom in for a little bit, you know, right, there is a triple intersection here for the region corresponding to, for the coverage regions corresponding to the sensors V2, V6, and V1, right? So that is one of the overlap regions. And then there is Where else? V6, V7, and V1, right? V6, V7, and V1, they also have. Where is this? V6. I'm coloring the triple overlap. Right, so V6. Yeah, okay, I guess that's fine. So those things that I shaded in black, that is where like there are like three intersections at once, right? Um, so that means that there would be like two solid triangles that you can draw in this picture as well. So that corresponds to, which would correspond to, so there would be two corresponding solid triangles, which I'll color in a moment. I guess I can color them like, so you can draw like kind of like a solid triangle for, wait, let me, you could draw a solid triangle for V2, V6, V1, right? So V2, V6, and V1. And you could also draw I'll use a different color for that other solid triangle. You could also draw a solid triangle for corresponding to V1, V6, and V7, right? Is that making sense, kind of? And you can kind of like see where I'm going with this, right? If there had been like a region where four of the sensor area coverage areas intersect, that would have corresponded to like a pyramid or like a tetrahedron. And if there had been a region where there's a intersection of five of the coverage regions, then that would give you, well, like that would give you the generalization of the tetrahedron, which would be like these five-dimensional, well, I guess four-dimensional simplex. But and that's kind of how you go in general. So like, so basically, like just to be more precise, you would say that a simplex, so in general, if the intersection of the, you know, of K of the coverage, if there's intersection, well, for K plus one of the coverage areas, there is a corresponding K-dimensional simplex, a standard simplex associated to this, determined by the vertices, and that does define a complex, a simplicial complex, which is called the check complex. So gives you the check complex. It does satisfy the closure thing because, if four coverage areas intersect, the only way for four to intersect is that, if four meet, right? Then like in triples, they also met, and pairwise they also met, like for an intersection to be non-empty, there must be an element that belongs to all of them, all of the subsets. And so if it belongs to all the subsets, in particular, if it belongs to four, it belongs to three, any of those three, or it belongs to any of those two, etc. So like the closure relation is kind of like not straightforward, but it's not too hard to convince yourself that the closure is satisfied. So the closure, because if the intersection, for example, if, for example, the intersection of four of the coverage regions is not empty, then there's, you know, then these three of these regions at a time can also not have like an empty intersection. Then three of these coverage regions, then any three of these coverage regions also intersect, right? It's kind of like, it literally is kind of like coloring. If you're able to color a tile with four colors, then the three of any of those four colors are always present in the coloring, or two of any of those four colors is present in the coloring, and so on. And any two also intersect. So yeah, it's better to think about it in colorings. Think about, you can think about the coverage as, think of the coverage regions in terms of colorings. If a point or a tile, if a tile gets covered, if a tile gets colored with four colors, then three of the colors are present, three of then three of any of those four. And any two, and any two, and so on. Okay, is that making sense? Okay. So again, like I think we should have time to come like later in the course, like talk about this coverage problem, because it's a fun application of many of these ideas. But like that is a nice way to think about it. Okay, so here's another example. Yeah, maybe let me describe this one because I think this one will take also a couple some time to describe, but it's like an important construction. So here's like another way. So here's another way. Okay, so this is how you use different colors. Think concentration colors. So okay, so for that I need to talk a little bit about Boolean functions, which are useful things as well. So a Boolean function, okay, so let me tell you what a Boolean function is. Well, that is a function whose input, so this is a function. Okay, do you want to start with, okay, I'll start with. So it's a function that depends on n+1 variables. So it depends. But each of those variables is like a Boolean variable, meaning that each of those variables can only be in two possible states, 0 or 1, each of which can be in only one state, in two states. Each can take two values, which for convenience you write 0, 1, right? And the output of the function itself, for each input, the value of the Boolean function would also be 0, 1. So it's like a 0, 1 valued function, So, and for each, and for each, and for each particular input, 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 parti the value of the function is 0 or 1. So typically, like in many of these cases, you interpret 0 as being the value false, right? And 1 as being true. So 0 typically stands for false, stands for false, stands for false, and 1 stands for true. So like, there are many, like even if you haven't taken like a course in logic, you kind of like know some of these classic ones. So one of the Boolean functions is like the not operation, right? So here's like a Boolean function. So here, like, I'll just draw some like two concrete examples. The not function. So typically, like the way it's been, those like the not logical connective is defined as be a truth table, right? So the idea is that so imagine you have a variable which I'll call x, and then I have not x, right? Which typically in discrete math or logic, it's kind of like drawn with that symbol. So for example, if x happens to be 0, means it's false, right? Not x is its opposite, so it should be true, right? So if x is false, its opposite should be true. And if x is true, right, its opposite should be 0, right? So you can just think of like encapsulating these as a function of a single input, right? So the function, the f naught function, I'll call it f naught, goes from 0, 1 to 0, 1, right? And it just like, f of 0 is 1 and f of 1 is 0. So that encodes the same information as what I just had there, right? It's just like more like from a function perspective in terms instead of a truth table. Is that okay so far so good? Now, and right in logic, right? In the usual sense, like for a proposition or for a statement to be true, for the if you say I like pizza and I like ice cream, for that to be true, I need both of those like sub statements must be true themselves, right? So you can also have like an and function. So here's another one, an and function. But now, is you're taking that when you build a sentence with an and, is and of two smaller things, right? So you have two Boolean variables representing propositions if you want, or statements, which I'll call x0 and x1 just to use that notation. And then the output would be x0 and x1, right? So again, like the idea is that, for example, if both are false, right? Then the and of two false things should be false, right? And if one of them is true, but the other one is false, that should also be false, right? And then if both are true, that's the only time where and is true. So here if you want to think of that's a truth table for and, right? And if you want to think about it as a Boolean function, it's just like it has to eat two Boolean variables and the output is 0, 1, right? So the f and as a function, you can, if you want to use Cartesian product notation, you can write it this way, meaning, there are two copies of 0, 1, right? Because it's two Boolean variables, and it produces something with values in 0 and 1. And again, like it just defined like in this same way, f of 0, 0 is 0, f of 0, 1 is 0, f of 1, 0 is 0, and f of 1, 1 is 1. In this case, there's a trick to write it more nicely, which is just like you multiply you know, you can multiply the variables, right? Because f of x0 times f of x1 would correspond to x0 times x1, right? I mean, just kind of if you think about this numerically, right? Because the only way for the product, if the variables can only take values 0, 1, right? The only way for the product to be 1 is if both are 1, right? So that is kind of like a way to summarize, the relation. But again, it's kind of like this way of summarizing the relation is more like specific to the fact that you're representing the true false values in terms of zeros and ones, right? Because obviously you could have used other representations. You could have used -1 and 1 to represent true and false. Like, there's nothing intrinsic about this formula. It's kind of more like specific to the fact that you're using it with zeros and one. But whereas here, this is kind of like more like about broad like a correct definition in the sense that it doesn't really matter, that you use zeros and ones to state it out, right? Is that okay? Is that making sense? So far, so good. And so how should I say this? Okay, so okay, so the idea is that the Boolean functions are actually related a lot to simplicial complexes. So every simplicial complex can be determined by a Boolean function that satisfies an extra condition, which is called monotone. So, okay, where should I start here first? Uh, so the idea is that simplicial complexes are closely related to Boolean functions, which are called monotone. So monotone in mathematics is usually like a word that you use when you want to say that something is kind of like either increasing or decreasing. So you call it like if it's always increasing or it's always decreasing, you would call it monotone. So in this case, what that means is that you have to give an order between the elements, and so you kind of use the usual ordering, which is that 0 is less or equal to 1, or the 0 is less than 1. So the idea is like a Boolean function is monotone. Okay. So what is okay? So a Boolean function is monotone. It's called monotone if the- okay. So let me write it this way: if f So let's say you have a Boolean function that's being evaluated to inputs. Okay, so one of the inputs I'll just call like x0, x1, x2 up to xn, and the other input is called y0, y1 up to yn. And so you say that one is not the function is monotone if the value of the function at this particular string, like also you can think of it as a sequence of like letters, right? Like, at this particular word is less or equal to the value of the function in this other word. If coordinate by coordinate, the entries are less or equal to the other. So whenever okay. So this is sometimes it is related to something called like the lexicographic order, like how do you order like words in an alphabet, you know, uh, and things of that sort. So what I'm saying, I mean, of course, like all of these variables, because they're Boolean variables, they'll only take two values, which are 0, 1, right? So what that's saying, like, is that if all the entries, um, um, if the values that you assign to all the Boolean variables are entry-wise less or equal to the values of the other variable, then the function outputs like a larger number for the second case. So let me give you an example of a Boolean function just to kind of make it a bit more concrete. Okay. So here's an example. I'll call this like the threshold function. So here's and okay, it's a little bit of a weird notation. I'll call it um 3, 2. Okay. So the upper number, the 3 just refers to the fact that it's going to be defined on it's always like something plus 1. So it's going to be defined on 0, 1 to the 3 plus 1 into 0, 1. So it's going to be a Boolean function that goes from 4 copies of 0, 1 to 0, 1s, meaning that it eats out its out its input is 4 Boolean variables. So again, like this 3 is just like for the last like index for the last Boolean variable because we start our indices at 0. Okay, so that's the 3 corresponds to that. Okay, and the idea is that if you feed it four Boolean variables, it will spit out a 1 if if the input has if two or more ones in the input. Okay, so this gives you 1 if two or more of the input variables are 1 and 0 otherwise. So again, I'll kind of like explain all of this in a moment. So like the first one is just like a combinatorics problem, right? If you have four variables, each one can be 0 or 1, right? How many possibilities are there for all the possible values of the variables? 2 times 2 times 2 times 2, right? Like 2 to the 4, 2 to the 4 is 16. So there are 16 possibilities for the input, right? Like the input can be one among 16 options, right? So I kind of like just write the 16 possibilities in a way that's convenient. Um, you'll see why I'm going to like list them in this way. So this is like the space of inputs, right? And this will be the corresponding output. So one of the inputs is just all zeros, right? 0, 0, 0. Okay. And then I'll list the next four. I'll use a different color because there's going to be a difference. Okay, this is like a tedious thing to do, but I think obviously I can work that out before. Otherwise, it would take me to forever to make sure like I'm doing it in the right order and everything. So this is okay. Then I'll put I'll put the next I think 9 or 10 in the different color, which would be 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1. Oops. Okay. Then where am I? I'm here. Okay. Okay. Sorry, I'll just go back to the next page and do it so that I have more space. And let me just erase it here because I don't um, maybe I need more space. Okay, so we're doing in this one. And 0, 1, 1, 0, 1, 1, 0, 0. Okay. Okay, so let's see how many we have here. Perfect. And then let's use another color for what comes next. And then we'll see why in a moment. Okay. Okay, I think that should be fine, right? Because how am I subdividing them? I'm subdividing them by I am adding up I add up the inputs, right? And I am classifying them according to the value of the sum, right? So the first one that is in blue, if you add up the numbers, you just get 0 plus 0 plus 0 plus 0, which is just 0. The next four are all the possibilities, right? That add up to 1, right? The next 1, 2, 4, 5. The next 5 are all the possibilities that add up. Did I miss that one? It's like 0, 1, 0. Let me check. Are you talking about the green ones or so? Oh, no, I definitely think that they'll. I'm just letting you go at least that like one. One. Oh, right. 1, 0, 1, 0. You're right. Thanks for catching that one. Okay, let me see if I can remove it a little. Yeah, because I mean, it's kind of like this 4 chooses 2 or something like that, right? So like it should not have been like an odd number, right? Yeah. So of course, like you can compute like with combinatorics how many you have to get from each of them, right? So 1, 0, 1, 0, right? Like that's the one you were saying. Perfect. Thanks. Okay. So then the next page Well, and of course it's symmetric, right? Like if you do it this way, because n chooses k, if you have taken combinatorics, right? N chooses k is the same as n chooses n minus k or something like that. So it's kind of like 1, 4, 6, 4, 1, right? So it's kind of, if you flip it around, the count is the same. But anyway, the point is that these are all the 16 possibilities for the input, kind of like breaking down into how much do they add up to, right? Like the values of the input. Okay, so this threshold number, right, basically reads out the input. If the input contains at least two ones, it spits out a one. And if there are fewer than two ones, it spits out a zero. So another nice way, a nice consequence of like arranging them this way is that kind of like in the first five, you get a zero, and then remaining ones, you get a one, right? So the output for the threshold function, right? So um, you know, all of these give zero output, and the next ones give one as the output. Okay. Which again is another nice consequence of the ordering. Um, of like putting it in this way. Okay. And like what it means to be monotone here is that if again, because you can think of each Boolean variable as kind of like on or off, right? True or false. So but what it means to be monotone is that if you kind of like change if you take one of the input values and you change a zero to a one, right? Because that's the only way to increase the value of an input Boolean variable, like just switching a zero to a one. Then the value of the function should be higher or like be the same. So it cannot go down. And it's kind of like easy to see here, like just because of like how it's defined, that if you turn 1 0 into a one, the best, I mean, you only have a chance of like increasing value of the function, right? Because you are getting more inputs that have a one. So this is like a monotone Boolean function. And okay. And what I'm trying to say is that there is a simplicial complex that I can associate to this Boolean function. What makes this fun is that it's reversible. So if you start with a random simplicial complex, you can also find a Boolean function that defines it. So it's kind of like a back and forth. So you can essentially think about simplicial complexes as Boolean functions with this extra property of being monotone. The monotone part is because of the closure relation. So I'll try to explain here. Um, uh, how the simplicial complex is defined. So, in this case, for the simplicial complex, what you do is you look at. Actually, let me write it in that previous page, and then I'll. That's the last thing I'll do today because I have to proctor exam later in a couple of minutes. So my claim will be is that if you're given are given a monotone. If you're given a monotone not monotone simplification complex, a monotone Boolean function, you can define a simplicial complex. So the way to do this, how do you do this? How to do this? Also, you consider, okay, so basically the idea is this. You consider all the input values, um, well, except the one that's just once, except one, 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 dot, 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 one. Like that, except the one that is just made out of ones. You'll see that in a moment. Okay. You consider all the input values whose output is one. Okay. And then the coordinates, the coordinates of this input, which were set equal to 0, define one of the simplices. Okay, so it looks a little bit, you'll see it's very simple in the example, but it kind of like looks a little bit weird, like the way I'm writing it. I'll write it down. I'll show you in a moment what I mean by this. But this is like the formula in general. Whenever you have a monotone Boolean function, this is how its simplicial complex is defined. The reason why it's kind of like nice to have a function around when you have a simplicial complex is that because there's like a version of the Fourier transform for Boolean functions, which is called like a Boolean Fourier transform, or like for a Fourier series for a Boolean function. So you can kind of like use that. We'll do that later on. For other things. But it is useful to know that if you have a simplicial complex, there's kind of like on the background a function, because with functions you can do things with functions, so you see like there are all the many different relations that kind of start popping out. So the simplicial complexes are really truly useful things. Okay, but let me explain to you how the complex looks like in this case. Yeah, in the remaining minutes, and then I have to add some more problems, but I will add some of these, like where I give you some simplicial complex, you're trying to find the function. It's like a useful exercise just to get like your hands dirty with some concrete things as well. Okay. Okay. So the construction of the complex is very simple. It says just okay, oops, sorry about that. First, just focus on all those inputs that give you value 1. Okay, don't worry about the ones that give you value 0. So you just, that's another nice thing about arranging them this way. So basically, we're just looking at all these inputs that start this number 1. Okay. Okay. So you have all these inputs. Oops. And at any particular of these for each of these inputs that gives you value 1, you look at the coordinates that were set equal to 0. Okay. So for example, in the first input, the first two coordinates were set equal to 0, right? And it's just that our coordinates start at index 0, right? So this would be coordinate 0 and coordinate 1. So you associate this, the edge, x0, x1. So I'll write down the kind of like the edge of the simplicial complex that's associated to each of them. So for this one, you associate the edge x0, x1, and then I'll do a picture in a moment. Okay. Then for the next one, right? The 0th entry is 0, 1, 2, 3. That's what you have to remember. That is such an annoying part because you start at 0. So 0 and 2 are the ones that have coordinate 0. So there's an edge, which is x0, x2. Then there's an edge for, x1, x2, right? Then there's an edge for x0, x3, right? The first and the last ones. Is that making sense how I'm kind of like identifying them? So again, you just pay attention to which one gives you 0. And then there's an edge for x1, x3. Okay. And then there's an edge for x2, x3. In fact, I wish I could, I think, oh yeah, I think I can change the colors here. Okay, so these are the edges that come from the green ones, right? These are the edges defined by the green, like, or the pieces of the simplicial complex defined by the green inputs. Then from the red ones, right? From the red ones, actually, that's where the nodes come from, right? Because they only have one 0 coordinate at a time. This one is x3, this one is x2, this one is x1, and this one is x0. So from the nodes, like the nodes come from the, you know, I'll do a more complicated, interesting example next time because this is just like vertices and edges. But of course, you could have tetrahedra and other things, and that's why you see like why you exclude 1, 1, 1 from the definition because I mean there's nothing there with zero coordinates, so it's kind of like the empty set. In a sense, like the empty set is always present in a simplicial complex, so like it doesn't make much of a difference whether you had it or not. But essentially, I'll come like just to wrap it up for today, I'll draw the picture. Again, the simplicial complex at an abstract level is just this list. That is what defines the simplicial complex. You don't need any extra information just to make it clear. Whether you want to make a picture of you, it's kind of like an additional thing to get some like extra geometric intuitions, right? But the complex itself, is just determined by, I'll write the vertices this way just to avoid another way to write the edges if you don't want to use the set notation is just to kind of like concatenate them, which is also convenient because it's a little bit faster. It's just that it doesn't matter in which order you concatenate them because, again, we're not thinking of the edges yet as being oriented. So it doesn't matter like in which order you write them. But that's another way to think about the edges. So for example, because I have four edges, I'll actually draw two possible pictures for how you could have represented it. So one picture you could have done is you put four vertices, right? And again, you connect 0 with 1. So I connect 0 with 1. I connect 0 with 2. I connect 1 with 2, right? I connect 0 with 3. I connect 1 with 3. And I connect 2 with 3, right? So if you draw the simplicial complex that way, that, I'm drawing all the possible edges, between those four nodes that are part of the simplicial complex, right? Those are not all the possible edges you could draw between those four nodes, right? But those are the ones that are determined by the function, by the Boolean function. Now, this is why I wanted to do the picture this way, because in this case, like if you draw it this way, like there are some artifacts of the representation which are not really there in the complex. Because for example, the way I'm drawing it, it feels like, oh, these two edges meet, right? It looks like there's an intersection, but that's kind of like a fake intersection. In the abstract complex, that intersection is not there because if there were like an intersection, there would be like a fifth vertex. So there are illusions that the picture creates that sometimes can be fixed by having like a better picture, but also that's why it's important to just think about the abstract level, which of course, like in data science or like more complicated networks where like things are 10-dimensional, 20-dimensional, you don't even try to do the picture. So like that's not much of a temptation. But especially when you're learning this at the beginning, you know, it can become like, an easy thing to fall for because, I think this should be fine. Yeah, so let's see. I think if you call this, here's another way you could have called these things. If you call this x3, I think, and then this is x0, x1, and x2. Here's another representation of the picture of the same simplicial complex, which is kind of like in a sense more accurate. So I think that the edges are okay. So x0 with x1 is here, x0 with x2 would be here, x1 with x2 would be here, x0 with x3 would be here, x1 with x3 would be here, and x2 with x3 would be here. So in a sense, that is kind of like a more, like if you wanted to think about this as representing like an actual shape or an actual space, this is kind of like a more accurate representation, the second one, because there are no spurious like or extra intersections, like fake intersections. So all that I'm saying, is that is something that you always have to take into account when you are want to think of these simplicial complexes as representing an actual space and things like that. That you have like a picture that is not making it seem like there are more relations that they're really as those as described as simplicial complex. Because again, if you think about it combinatorially, they both have the same information. It's just that the one on the left side seems to again suggest that there's like a fifth vertex which is not there, right? So that's why it's important to always kind of like have make kind of this clear that for us the pictures are kind of like that's a sort of aid, but it's not everything can be defined like algebraically in terms of like the formula. Which I'll start giving you next time, but I'll still want to discuss some other examples. But hopefully, kind of like this one is interesting enough that you start saying, "Oh, this actually is related to other things." I think next time what I'll do is kind of like go backwards. I'll start with the simplicial complex and then tell you how to find the boolean function, which is also like fine. But yeah, let's finish here because I have to go after come to exam, so I should get there a bit earlier than usual. And then next time we'll continue some examples and other things like that.